to everyone. Good day to everyone joining this webinar from all around the world. So critical transitions in complex systems, or what we call CTCS webinar series, is being jointly hosted by IIT Madras in India and Potsdam Institute for Climate Impact Research, PIC, in Germany. This seminar series brings together experts from fields, a wide variety of fields such as climate science, fluid mechanics, neuroscience, ecology, etc., and aims to disseminate the state of the art and the prediction of critical transitions and these diverse fields of study using a variety of tools. The seminar series usually takes place every month on the last Monday of the month, so mark your calendars. Before we introduce the speaker, a few housekeeping notes. I request everyone to turn off their microphones. There will be enough time in the end for asking questions, so please type your questions in the Q&A box in Zoom to ask the speaker your questions. There will be enough time at the end to discuss your questions. Now I request Professor Jürgen Kurz to introduce the speaker, Professor Ambika.
Okay, yeah, thank you very much, Sujit. And I'm again very happy that we can continue our very lively webinar series with Professor Ambika. I think most of you know her very well. She has been contributed a lot to nonlinear dynamics as well as applications. I remember when we met, you were mainly studying nonlinear data analysis techniques, and also not only the techniques you develop, but also very interesting applications, biology, stock market, and even astrophysics, black holes, which I always admire. And you could publish there in the best astro journals these findings, which is not easy. And then you turned more to complex networks, synchronization, and especially to not so simple complex networks and special phenomena as amplitude death, some anti-synchronization, if you wish, and now more also so to several layered networks, and one specific type are multiplex networks. And I'm very interested to listen your recent results about this. Please, Ambika.
Okay, so let me start by saying good morning, good afternoon, and good evening to all those who have joined from different time zones. And thank you, Jürgen, for the very nice introduction. And thanks to Jürgen and Sujit for inviting me to give this webinar today. I have been enjoying this webinar series since its very beginning, and I have been attending almost all of the webinars, and I really enjoyed them. And now today I will talk about some emergent dynamics and dynamical transitions that can happen on multiplex networks. Let me start by briefly explaining the plan of the talk. I will only touch upon three aspects. One is some interesting dynamical emergent dynamics that can happen on multiplex networks, taking some specific example of neuronal networks. And then I will talk about some dynamical transitions, specifically tipping, which means sudden transitions, which happens because of multiplexing, and then explosive synchronization on multiplex networks. And towards the end, I will talk about how we can control these transitions as well as the dynamics, explosive to continuous transition, recovery of oscillations from some of these interesting states like chimera and suppressed states. And if time permits, I will also talk about relay synchronization and controlling amplitude of oscillations in a relay setup. So just to introduce these multiplex networks, we know that the complexity of real-world systems can be modeled by complex networks. So these complex systems then consist of interacting subunits, and the complexity arises from two or three factors. One is the nonlinearity in the intrinsic dynamics, and then complex way of or pattern of interactions among them. And of course, there can be variability and heterogeneity of the subsystems and the connections in a real-world scenario. This will add another level of complexity. And I will touch upon another level where we have heterogeneity, which comes from differing dynamical timescales of these connected systems. In all these cases, an effective model will be to represent them using multiplex networks. And multiple timescales can occur in complex systems in many cases, which is very natural and realistic. I'm giving some examples here. Electrical activity of neurons, chemical reactions, turbulent flows, population dynamics, especially climate, where you have atmosphere and ocean having two different timescales. So in all these cases, the emergent phenomena will depend not only on the connection and topology of connections and intrinsic dynamics, but it will also depend on the dynamical timescales. So I will try to show some examples where this can be illustrated. So talking about multiple networks, they give additional flexibility and tunability in our modeling. This is because if you have a set of systems connected using two different types of interactions, you can separate them out as two levels, two layers, one layer having one type and the other the same, other having the other type. And between the systems, we connect these eye-to-eye connections we make, which makes them a multiplex network. So this will be more realistic because in a real-world scenario, you have different types of interactions and different types of systems. And then the topology of each layer in the multiplex network can be of different types depending upon the context. A simple case will be they have the same topology, but they are separated into different layers and connected between them. You can also think about different topology, different type of network here and here, layer 1 and 2. And this color means different color means they can have different type of dynamics also. As a specific case that I will consider, I think about a ring network where in one layer there are only local interactions or nearest neighbor interactions, while in the other layer it can have non-local interactions, and the dynamics in this layer and this layer can be different. You can extend it to 3-layer multiplex networks or any number of layers like that. But I will stick to 3-layer maximum, where the central layer is connected to the other 2 layers L1 and L2 by multiplexing. And as a specific example, I will take up a case where you have the central layer connected to the 2 other layers, but they are not connected, which means the interlayer connections are directional, unidirectional. So in a way, the central layer now is the drive, and the other 2 layers act as responses. This is a specific case where we can have some interesting results, which I will try to show. And talking about the emergent dynamics that can happen in such a setup, the most well-studied and well-established emergent behavior is synchronization, where you have different types of synchronization, complete, phase, or frequency. We can also have suppression of oscillations, which are called homogeneous steady state and inhomogeneous steady states in the complex network. And of late, we have another interesting pattern or spatiotemporal pattern that develops in this context, which are called chimera states. These are partially synchronized states where coherence and incoherence will coexist. So I'll be mostly talking about this type of interesting chimera states that can happen. And chimera states are found to be useful in many natural setups like neuronal networks. It is suggested as a mechanism for epileptic seizure, and then they are associated with the hard to model ventricular fibrillation. Of course, the hemispheric sleep of mammals and birds, and also in technological networks like power grids and social systems where you can have 2 types of populations with partial consensus, etc. So these are all cases where chimeras are really prevalent. And a variety of chimeras have already been studied in the context of complex networks, where one or two specific cases that I will consider in today's talk are amplitude chimera, where the coherence and incoherence occur with respect to the amplitude of the oscillations. They oscillate periodically with the same frequency, same phase, but they have different amplitudes. And if they correspond to steady states, which are coherent and incoherent, we call it chimera dead state. Then of course you can have multi-chimeras, frequency chimera, etc. But I will touch upon only the first 2. And to consider such a setup, I talk about 2-layer multiplex network, where in which case one layer consists of systems which are interacting among themselves, and the second layer consists of external systems, which I call as the environment. So this environment is modeled as a system of coupled elements where they can communicate to each other or through signal molecules or dynamic agents, which can be a surrounding medium through which they diffuse. So our layer L1 is an ensemble of identical oscillators interacting directly through local coupling. And then the layer L2 is a set of dynamical agents which are connected in such a way that they are non-local connections. But the interesting thing is this second layer has no dynamics on its own because it is sustained only by feedback from the first layer, and then they can influence the first layer through a feedback coupling. So this is a setup which I have already shown. We have a ring network where we have all these oscillators or system network, let us say. The other network layer L2 is the environment network. This is non-local connection. Its dynamics is different. This is local connection. So as the local system, I am considering a Stewart-Landau oscillators in the limit cycle with the limit cycle dynamics. So this part of the equation deals with that. And then you have these connections which come, the intra-layer connections between the oscillators in the layer 1. This is second layer, which as I said is a heavily damped oscillator type, but it is sustained by feedback from the other one. This is the feedback term. And among themselves, they are again connected with non-local connections like this. So we have short range interactions in L1 coupled to another system of systems which have long range interactions. So these non-locality or long range interactions in L2, we find can induce and control the chimera states in the other one. So I will just illustrate that using some spatiotemporal plots, which is very easy to show. In the first case, we are having synchronized oscillations. So these different states are possible in L1 as you tune the interlayer coupling strength, which is denoted by this epsilon. So for very small values of this interlayer coupling strength, we have synchronized oscillations in L1. But as you increase it, we find that amplitude chimera sets in. As is clear from this, there are incoherent states as well as coherent states coming in. And if you further increase epsilon, you have inhomogeneous steady state coming in, because as you can see, they are going to steady states, but they are not always of the same type. But if you increase it further, you find homogeneous steady state, which again will go to one state chimera death, which means you have a death state or steady state here for part of it, and the other corresponds to another steady state, which are not coherent. Now we can further increase epsilon to get two-state chimera death, which means part of the oscillators have one state, the other part has another state. In between, we have states corresponding to both occurring in an incoherent way. And of course, to get this, we have to give some specific initial conditions. So if you are considering 100 oscillators, 50 oscillators are given initial conditions in the positive side, and 50 are given on the negative side, and around random, and they are made random around that. And similarly, the second layer anyway is a uniformly distributed random numbers. That's what the type of initial conditions that you give. So just to illustrate the case of amplitude chimera, when epsilon is small, they have synchronized oscillations, which means if you plot all of them together, they fall on top of each other, giving a single limit cycle like this, completely synchronized state. As you increase epsilon, you get amplitude chimera, which means a number of oscillators are still synchronized, but you have others which have different amplitudes and which are not synchronized with the others. Now, rather than plotting spatiotemporal plot and these phase portraits, there are some quantitative measures that are usually used to detect chimera state. One is called the strength of incoherence, which was introduced by Professor Lakshmanan's group earlier. So here what we do is we take the difference between two adjacent oscillators as Wi, Li. Then we divide all the oscillators into bins of m bins of size n like this. And for each one, we calculate these values and then take the standard deviation defined like this. And from this standard deviation, we will define a strength of incoherence as given by this, where Sm is given counted like this. So if they are incoherent, all the oscillators are incoherent, which means the standard deviation will have some finite value greater than this delta. This delta is normally fixed as a very small value. I have taken it as 0.2. And therefore, Sm will be 0 and then S will be 1. On the other hand, if they are all coherent, this is always 0. The standard deviation is always 0. And hence this Sm here calculated will be 1 for whatever small value you take for delta, which means S is equal to 0. And for chimera states, it lies between 0 and 1. So you can calculate and plot the strength of incoherence versus epsilon and then detect positions or values at which you can observe different types of chimera states. And also to distinguish between one-state chimera death state or two-state chimera death state, again, Professor Lakshmanan's group has defined a discontinuity measure, which is actually calculated based on the distribution of these SM values as shown here. This will be 1 for one state chimera death state and 2 for two state, etc. So these multi-state chimera death states can also be identified using this measure. And once you have done that, calculated these measures for different combinations of parameters, you can have a complete picture of all these possible dynamical states on these parameter planes. I am taking the range of non-local connections in the second layer versus epsilon in the first one, and then the intra-layer coupling of the second layer versus epsilon. Also, the intra-layer coupling of the first layer versus epsilon. These are the important parameters that ultimately decide the final emergent state. And I have listed here all possible states and then shown them by color on this. So it is good to understand that a wide variety of dynamical states are possible by tuning the parameters. But interestingly, if the first layer is also having non-local interaction, then we find most of these chimera states are suppressed. For epsilon equal to 1.6, we still get amplitude chimera, but as you go on increasing, you get only multi-cluster steady state, then homogeneous steady state, and two cluster steady state. These are the only states possible because the other chimera states are all suppressed because now we have made L1 also non-local in its interactions. So this is once again showing the parameter plane, showing all these different types of behaviors. As you can see, the amplitude chimera region is now very, very small, and most of these regions are occupied by these two-state chimera, cluster synchronized states, etc. Now, we can even think of some extreme cases, no coupling in layer L1, non-local coupling in L2. Then you have only homogeneous steady state and two cluster steady state. As we said, you can make L1 non-local, L2 local. Then you have complete synchronization and then inhomogeneous steady state and two cluster steady state. Also, L1 non-local, L2 no coupling. Then you have multi-cluster steady state. And synchronized states occur for low coupling strengths in all these cases. So by adjusting the range of interaction in the different layers, as well as the interlayer coupling strength and the intralayer coupling strength, it's possible to see a wide variety of dynamical states emerging on these networks. Now I will take a specific case of a neuronal network where these type of patterns are very relevant. And then one case that I will consider is neurons in one layer are coupled with excitatory coupling, synaptic coupling, and the other layer coupled with the inhibitory synaptic coupling. In the context of neurons, these two are very relevant. And then these neurons can interact electrically also and synaptically also. And I will consider one such case also. And the interesting result in this case is the activities patterns can emerge and get selected across the layers as we change the parameters. So as for the model, a single neuron, I am using this Hinmarsh-Rose model or HR neuronal model as shown here. And then I am having coupling strength between this intralayer coupling as well as feedback coupling between the layers as shown here through this epsilon. And the other parameters chosen for the Hinmarsh-Rose model as shown here. And then we can see that in the absence of interlayer coupling, if each layer is independent, L1 with excitatory coupling can have two different interesting states. One is a completely synchronized state, which happens for a large coupling strength. But however, the intrinsic bursting pattern is changed now to another type of bursting. But if you further increase the coupling, you find it will go to a state of no spikes or its suppressed states, which we can call as an amplitude death state. While the second layer, which we have taken with inhibitory synaptic coupling, we find anti-phase synchronized oscillations are possible. So even numbered ones show one type and they are completely synchronized, but odd numbered ones have anti-synchronized with the even numbered ones. So this is the specific behavior without multiplexing. Now I multiplex them. That means I take a non-zero value for epsilon. And then we find that the activity pattern that is there in the layer L2 is copied or transferred to layer L1 also. That is what is shown here. So there's a transfer of dynamical patterns from L2 to L1. So this is, in a way I understand, is because the intralayer coupling in L2 is higher than that in L1. In fact, in this case, I have taken no coupling in L1. Now, even if you have some coupling in L1, if it is very small, and the other coupling is higher, then that particular activity pattern will be copied to the other, and vice versa. Which means if the coupling in the first layer is very strong, like 3, the other one is very small, and then these in-phase oscillations that are there in that layer will be copied to the other layer also. So there is a transfer of these patterns of activity which is possible, and in the context of neurons can self-organize by adjusting all these parameters and then select a particular activity pattern on both of them. In fact, we can use this for reviving the activities in L1, because I said for high coupling strength, there is suppression of oscillations in L1, which we can revive by multiplexing. Similarly, the in-phase oscillations can be made in L2 by coupling by multiplexing. And then we can see this anti-phase or anti-synchronization becomes in phase. We can also see a transition from in-phase to anti-phase. Suppose the coupling in L1 is stronger, which means L2 is also in in-phase oscillation. But now if you go on increasing the coupling in L2, then you find there's a sudden transition from in-phase to anti-phase. So this is very clear because now I am plotting this average phase difference here and then showing it as a function of lambda 2. Similarly, the suppression of activity on increasing epsilon can also be seen by plotting the average amplitude. This I am showing for one layer, same thing can happen in the other layer also. So the amplitude initially increases, then it goes to a different type of burst pattern, and then suddenly goes to a state of amplitude. So this is also an interesting transition that can happen, which is a sudden transition. Now I talk about dynamical transitions. We already talked about some transitions in the networks here, but I'll again talk about some sudden transitions that can happen because of multiplexing. These two types I will consider provided I have time, and explosive synchronization that can happen. First thing is tipping that is induced by multiplexing. So here I am considering one layer which is already having a sudden transition to a steady state due to its indirect coupling with a shared environment. And then this is multiplexed with another set of systems. Then we find the tipping is happening in the second layer also. So this is the set of equations that I have chosen for that. Here we can consider any type of topology. I have taken scale-free topology as well as regular network. This is the topology adjacency matrix deciding the topology of the other network. And then we have diffusive coupling in intralayer, and then we have this type of coupling. This is the type of feedback coupling. Between the layers also, we have having diffusive coupling here. So then we find that as nodal dynamics, I am considering Van der Pol oscillator, and we can consider scale-free as well as regular type of networks. And then coupling can influence transitions between them. So here we are actually considering tipping from oscillatory state to death state. So we have to have an order parameter, which is some sort of a measure for the average amplitude, which is defined like this. And the ratio of this amplitude with respect to the intrinsic amplitude is taken as the order parameter in this case. And using this order parameter, we can actually trace the type of transition. And then we can even check by doing this adiabatically, by increasing this coupling strength adiabatically, we can check the forward transition as well as the backward transition. So on the left side, I have the transitions happening on layer L1. On the right side, the same transitions are happening on layer L2. So whatever is happening on L1 at the same parameter value is copied in the transition is happening in the other one also. And oscillatory state to death state happens when we have L1 and L2 with scale-free topology. In this case, when you have scale-free topology, we can consider topology with different values for the average degree. If it is 6, we find that there is hysteresis. But as you increase this to 20, for example, in layer 1, the scale-free topology is such that its average degree is 20. Then you find that the transition is happening, but without any hysteresis. So this is once again this parameter plane of this average degree versus this coupling strength, where we can see where hysteresis can happen and where there is no hysteresis, and then oscillations are happening in the other one. Now, if you consider a topology not scale-free type, but with non-local connections on a ring type of topology, in this case also, we find transitions happening induced in the second layer by the first layer when there is multiplexing. But in this case, as the range of coupling in this second layer increases, we find that again hysteresis is not there, but it's a sudden transition without hysteresis. That's what is happening. So we can consider different topology, different types of coupling like mean field coupling, conjugate coupling, etc., and heterogeneous topology. So this is just to illustrate different types of possibilities, which I am not showing for want of time. But now I will talk about another type of explosive transition that can happen, which is called explosive synchronization. This is a type of sudden transition to synchronization. Here, for this, I am taking L1 as coupled with attractive coupling, L2 coupled with repulsive coupling, just like the neuronal case I have considered earlier. But here the dynamics is Stewart-Landau oscillator, and I will also show Fitzhugh-Nagumo oscillator, which is again a neuronal model. And then we can have couplings of the mean field type or some for intralayer coupling, different types are possible. So this is a general type of equation that I have written. Here lambda A, this means attractive coupling. Here this means repulsive coupling. Then we have explosive synchronization happening in the presence of little bit of Gaussian noise added. And transition is with hysteresis to a state of complete intralayer and in-phase interlayer synchronization. Now, the width of the hysteresis depends on the range of this attractive coupling as well as noise and strength of interlayer coupling. So there are some parameters in all these cases which you can tune and make them have any desired type of transition as well as emergent dynamics. So with Stewart-Landau oscillators, these are the equations which I have shown. L1 is attractive coupling, which is non-local. L2 is repulsive coupling with non-local. And the sudden transition that is happening in this case is to synchronization, which means to measure that or to detect that you need another quantifier, which is the average synchronization error, which is defined like this. So for any such sudden transition or tipping to happen, we always need some sensitive state. So in this, some heterogeneity or asymmetry or perturbation. So in our case, we achieve this by making this coupling attractive and repulsive with non-local coupling. And then in the absence of noise, you find that the transition is sudden, but there is no hysteresis. But if you add a little bit of noise, the noise is very little at gamma equal to 0.001, we find that explosive transition happens with hysteresis, with this attractive and repulsive. And this is, we are showing it for two cases. When you have the range of coupling in the first layer as 25 and we increase it to 40, in both cases we see it. Exactly the same transition happens in L2 also, so that I am not showing here. But now we can think of different types of coupling, mean field coupling. For this intralayer coupling, we make it mean field. Then also we see that transitions happening. Two cases I am considering. These cases also, the transition is sudden with the hysteresis. And then we can think of Emergent oscillators, Fitzhugh-Nagumo oscillators with attractive and repulsive coupling, with non-local coupling and mean field coupling. These are just a variety of cases for which you can apply that. Now I come to the third part of my talk, where we talk about control of dynamics and dynamical transitions. So two cases, or in fact, three cases I will consider. One is we have a transition. We want to see whether we can control explosive transition to continuous transition. And we will also see whether we can remove these chimera and other oscillation suppressed states and recover the synchronized oscillations. I will also consider a case, as I said, where we have the interlayer coupling is directional, which means only unidirectional, not both ways. Then we can have relay synchronization, where we can have control of amplitude of oscillations. So these are all different types of control strategies one can adapt. First, let me talk about control of explosive synchronization. So we said that there are instances where synchronizations are very sudden or explosive, but this need not always be a desirable effect. If it is undesirable, we should be able to control it. So this is proposed as a potential mechanism for some brain disease called hypersensitive fibromyalgia. So, and also this is related to cascading failures in power grids, transitions in electronic circuits, loss and recovery of consciousness in anesthesia. So in all these cases, controlling this explosive nature to continuous transition is very relevant. So nature of transition change to continuous type is possible by tuning the couplings or by increasing or decreasing the noise strength, all these things. I will consider 1 or 2 cases here. So in the earlier case where we have these coupled Stewart-Landau oscillators with attractive and repulsive coupling, we find that by increasing the strength of repulsive coupling, we can have a transition change from this sudden transition with the hysteresis is now changed to a continuous smooth transition. So this is the same transition happening with the increase in the attractive coupling, but we are keeping the repulsive coupling at a higher value. Similarly, we can increase the noise strength gamma. Then also we find the sudden transition with hysteresis is gone, because as you increase the noise strength, what we find is the width of this hysteresis goes on reducing, and finally it will become a continuous transition instead of a sudden transition. So these are 2 ways of controlling explosive nature to a continuous transition. Now coming to the second type, where we want to suppress the chimera state. So once again, I am taking the same framework which I started with, where we find amplitude chimera and different types of chimera death states can happen. And in these cases, now the only difference is to the second layer, which are these environment or dynamical agents. Now I am adding a small parameter tau here, which essentially is a time scale, introduces a time scale difference between the 2 layers. So if you have a value of tau which is less than 1, which means the dynamics of the second layer, which is the environmental layer, is going to be slow. It will be slower than the other one. So this slowness parameter can be tuned and adjusted in such a way that we can control the type of the emergent dynamics on the other layer. So let us consider a few cases. So we already talked about amplitude chimera happening in the layer 1 earlier. And if you take tau is equal to 1, that means there is no time scale mismatch. This amplitude chimera is what we have earlier seen. Now, as you go on decreasing tau, making it 0.4, for example, this amplitude chimera is gone and we have all synchronized oscillations coming. Even for smaller values like 0.1, you find synchronized oscillations are coming back, or they are recovered in the layer 1. Similarly, for a higher value of epsilon equal to 3, we already had inhomogeneous steady state like this. Now from this inhomogeneous steady state also, by decreasing the value of tau or by making the environmental layer slower, we can recover the synchronized oscillations in layer L1. And I also consider 2 more cases where we had homogeneous steady state. So here we find when you decrease it up to 0.4, also it is homogeneous steady state, but further decrease to 0.1, it goes to synchronized oscillations. And in this case, here we have one state chimera death state. And from this one state chimera death state, we can tune the parameter tau, and then it first goes to homogeneous steady state. And from that homogeneous steady state, it goes to synchronized oscillations. So this is actually tuning the timescale mismatch between the layers, and then we are able to recover the synchronized oscillations. So this can be further studied by calculating the average amplitude of oscillations. And then we find that the average amplitude of oscillations initially was in the suppressed state, that is inhomogeneous steady state. And this one more thing to notice here is that this transition is very sudden. As you increase tau, at one point, it suddenly goes to a state of non-zero value for the average amplitude. The green one for layer L2 and the blue one for layer L1. So we can see how synchronized oscillations are recovered. And a few more cases where I am just showing the results. This is 2 states. We had a state of 2-state chimera death. By tuning the parameter tau, we find that it first goes to a 1-state chimera death state, and from there it will go to homogeneous steady state and then to synchronized oscillations. It will pass through these in-between states and then go to synchronized oscillations. When both layers have non-local coupling, we can have traveling waves. From that also synchronized oscillations can be recovered. And when you have multi-cluster steady state also, we can recover synchronized oscillations. So the dynamical time scale has a role to play here. And then these different dynamical states, once again, I am showing in various parameter planes. The first one is for tau equal to 1, which we have seen earlier. Now we have reduced tau to 0.5 in the second figure. And as you can see, the region of complete synchronization has increased now. Now, the third one is the most relevant one, where you have the time scale mismatch on this axis and the coupling strength on this axis. And then you can see as the time scale mismatch decreases, we have a larger region where you can get complete synchronization. This can be extended to a 3-layer multiplex case where you have the central layer L2 behaving as your environmental layer, and system layers are L1 and L2. Again, local coupling here, non-local coupling here. So these equations are written here. And this second layer, which is now this environment layer, has this parameter tau, by decreasing which we can make that layer slower. And then by tuning that, we can adjust the emergent dynamics, or we can control the emergent dynamics in L1 and L3 to different possible values. I'm just illustrating one case where when you have epsilon equal to 0.4 and tau equal to 1, there are oscillations in both the system layers 1 and 3, but they are anti-phase to each other, as you can see. But if you tune this parameter and make it very small, like 0.1, then you find that synchronized oscillations are recovered. So now both layers L1 and L3 have synchronized oscillations, as we can see. So this is again shown here by calculating the phase difference between L1 and L3. And as you change, because as you can see for tau equal to 1, they are anti-phase. And then suddenly for one value, there is a transition to a state where they become in phase. So this transition is again from in anti-phase to in phase, and it is a control by tuning this parameter tau, which is a timescale mismatch between the two. And few more cases, when you can have homogeneous steady state, we can bring back oscillations. From inhomogeneous steady state also, we can bring back oscillations by tuning the parameter tau. Now I come to the last part of the talk, where I talk about multiplex network, where the interlayer coupling is unidirectional. So such type of unidirectional couplings have relevance in many real-world scenarios. We find that such network structures can be found in social interaction networks, power grid networks, etc. And in neuronal networks also, we find that the thalamus can act as a relay between distant cortical areas through thalamocortical pathways. And of course, epileptic propagation we usually study in unidirectionally coupled networks. One is the disease spreading network, and the other is the social connection network. So information from this layer can be transmitted to the disease spreading layer by unidirectional coupling. So one network coexists in functional relation with another in this case. And then we find that this can be considered as the concept of generalized synchronization, generalized to the context of networks. So this is the type of schematically I'm showing this. Here it's the same thing. You have a central layer and two other layers, response layers. Because the directional coupling is directional, we now call the central layer as the drive layer and these two as the response layers. So schematic, this is a general equation which is shown here for any type of dynamics F on these layers. And then we have this intralayer coupling as well as feedback type of interlayer coupling, which goes from the drive to both the response layers. Now the equations are written in full for the specific case when you have Stewart-Landau oscillators as the system dynamics and unidirectional interlayer feedback coupling. So this is self-explanatory. But in this case also, for the central layer, I am keeping a parameter tau, so that I can later show that by tuning this timescale mismatch, how the nature of the dynamics can change and we can have different type of desired dynamics on the other two layers. Now, the first thing that we notice is that there is a relay synchronization in this network, which means these two distant networks L1 and L3, which are not directly connected, they get synchronized with each other with the help of this intermediate network, which is acting as a relay. So as you can see, we are showing the time series of the X values, blue for layer L2, which is the drive, and the other red one, and you can't distinguish them because they are falling on top of each other. So there is relay synchronization between L1 and L3, but the interlayer synchronization with L2 is only in phase, as you can see. So here, there is coupling strength, large coupling strength for layer L2, which means it is already in a synchronized state. While the coupling strength in L1 and L3 are very minimal, so left to itself, they will not be able to synchronize. But this relay from the drive makes them synchronized, and both of them become completely synchronized also, and synchronized with each other also. Now we need two quantifiers. One is synchronization error for the intralayer synchronization, which is as we have defined earlier. Now we want another synchronization error for the interlayer synchronization, which is also shown here. We take it between two layers here. This is within one layer. So then we can see how the drive and response layers get synchronized to each other. So here I am showing this intralayer synchronization error versus interlayer coupling strength. But as we said, the drive layer, we already took it to be high value for coupling. So it was already synchronized. The error is 0 throughout. While the response layer shown in red and green, they achieve intralayer synchronization only with increase in the value of epsilon. That can be K. Now this interlayer synchronization error between the response layers, which is blue, goes to 0, indicating relay synchronization. Our interlayer synchronization error between the drive and the response layers, you see, that's not going to 0. In fact, that goes on increasing. This is because whenever this relay synchronization happens, there is an amplification also in the response layers. You must have noticed it here itself, because the amplitude of oscillations in the response layers is much higher compared to that in the drive layer. So because of that amplification, the interlayer synchronization in between the two layers L1 and L3, it is there, but with respect to the central layer, it is not 0, but it's steadily increasing. So how do we again measure that or detect that? For this, we define an average amplitude like this, which is defined like this, and that is plotted versus epsilon. So here we find that with respect to increase in the interlayer coupling strength, the amplitude of the response layers are equal and they increase, while that of the drive remains the same. Because we have only directional coupling, the drive is not affected, but the amplitude of oscillations in the other two layers are increasing as we increase this. So which means there is a control on the dynamics also now, because we can have amplitude increasing. Now, between the layers, we find there is phase synchronization between the drive and the response layers. To check that, we calculate the average phase difference between L1 and L2, which is shown in red, and that between L2 and L3, which is shown in green, with increasing epsilon. So you can see that this phase difference goes to 0 as epsilon is increased. So between the layers, drive and the response, it's always in phase synchronization, while between the response layers, it is complete synchronization. Now, we said that by increasing the feedback coupling, type of coupling between the layers, we get an amplitude, increase in the amplitude or amplification in the response layers. But sometimes that amplification may not be required. We would like to synchronize its amplitude also with respect to the drive layer. Then what we have to do is, we can control the amplitude as well as the frequency of the response layers by adjusting the timescale mismatch. As I said, in the central layer, I have kept a timescale mismatch also. But now I am making that central layer faster, which is equivalent to making the response layers slower. But the central layer is the one which is with us for controlling. So therefore, I'm increasing the mismatch parameter there to 2.5. So then you can see that their amplitude become the same. The frequency is also changing. And then we can slowly tune this parameter tau until we have a modulation of the desired modulation for the amplitude and the frequency. So the relay synchronization now happens with equal amplitude and frequency as the drive. But the interlayer synchronization now becomes only frequency synchronization, that in-phase synchronization is not there. Now, suppose we further increase this parameter tau, we find that there is a change in the dynamics also happening. As you can see, we are plotting the time series of the x variable here, and then we find that in the phase space portrait is also shown, which means we can see relay synchronization with amplification in the first case where your parameter tau is equal to 1. But by adjusting the parameter tau, we find that we can make their amplitudes the same, but then there is no synchrony in phase, but their amplitudes are the same. But if you further increase, we are introducing additional time scales, then we find that quasi-periodic behavior is seen on the response layers. So, but then there is no synchronization between the layers, as there is only behavior of frequency synchronization. So with this quasi-periodic thing, there is only frequency synchronization and there is no higher level of synchronization happening. So all these are condensed into this parameter plane I am showing. Here the relevant parameters are the timescale mismatch tau as well as the interlayer coupling strength epsilon. You can see that amplification of the response happens in this region. Equal amplitude oscillations can be done by adjusting the epsilon as well as tau. But there are smaller amplitude oscillations happening as you go on decreasing tau or increasing epsilon. And then we have a region where you have quasi-periodic oscillations happening in the response network. So with diffusive interlayer coupling also one can try, because here I have taken feedback type of interlayer coupling. When you have diffusive type of interlayer coupling, the response layers are always in complete synchronization with the drive and the whole network is synchronized. In that case, when you make the drive faster by adjusting tau, suppression of amplitude is happening in the response layers. I am not showing all details for want of time, but these are the main results in that case. Now we will like to extend this to a 3-layer case. We can do it for Stewart-Landau oscillators also, but I am showing this for the interesting case of a Rosler system with diffusive coupling, because we can then consider periodic oscillations as well as chaotic oscillations. So this is the Rosler system, which is, there are 3 layers of Rosler systems as you can see, with coupling K1, K2, K3. Interlayer coupling, intralayer coupling is diffusive type, interlayer coupling is also diffusive type. And in this particular case, we can see some interesting behavior like this. One is in the case when you have epsilon 0, which means there is no interlayer coupling, the layers L1 and L3 are independent. Then, as you can see, since we start with random initial conditions, even though the Rosler system is in the periodic regime, there is no synchronization among these oscillations. But the coupling in the central layer is taken to be high enough so that there is synchronization in that layer. But now when you increase epsilon to 1, you find that we can have synchronization in the other 2 layers, the response layers also. And then they are all completely synchronized. So we have this 3-layer network. All in period 1 cycle, we have chosen the Rosler system. The drive can synchronize the response network with complete synchronization in all the 3 layers. Now we consider another interesting case where you have 3-layer multiplex network, but Rosler system is in the chaotic regime. So in that case, what happens is the response layers on the response with periodic systems as the drive layer. So the drive layer has the periodic Rosler system, while response layers are chaotic by increasing the parameter, its intrinsic parameter to 18, while the other one has parameter 4. And the main result here is the drive brings the response networks also in the response networks in the chaotic dynamics to synchronized state. So as you can see here, the response networks also now have a periodic behavior. But interestingly enough, this periodic behavior is slightly different from the intrinsic periodic behavior of the Rosler system, as you can see. So here the drive response layers are chaotic, but here by increasing epsilon or introducing multiplexing, we find that the response layers have periodic behavior, but it's different from that of the intrinsic system, which means that if you plot this drive as well as the response layers like this, you find they form a closed curve. So this is reminding us of the framework of a generalized synchronization, where there is a functional relationship for the response layers with the drive layer. So if you remember the auxiliary system approach that is usually used for studying generalized synchronization, this is almost the same as that, because you get a functional relationship between the response layers, and the response layers are synchronized between themselves, but functional relations with the drive layer. So this we can say is some setup which is reminiscent of the generalized synchronization, but in the context of a complex network. Now I can increase this to any number of systems added on both sides. I'm just illustrating one such case where you have a drive layer here And now we have one more layer added for relay synchronization. Here also one more layer added. So we have totally 5 systems, 5 layers now, L1, L2 on one side, L4, L5 on the other side, and all interlayer connections are directional. So in this case, also we find relay synchronization between L1, L5, these two, and between L2, L4. And interlayer synchronization is in phase type. And amplification of the response layer can be tuned by increasing tau, and then we observe quasi-periodicity by tuning tau. So I'm just indicating them. I am not showing all the details for want of time. And I think with that, I am almost concluding my talk. I didn't keep a summary slide because I have almost always summarized my results earlier. But I would like to acknowledge 2 students who have worked with me in all these results that I have shown. One is Dr. Umesh Kumar Verma, who was a postdoctoral research fellow with me in IISER Tirupati. He is now in Central University of Rajasthan. And the other is Ivan Vadakan, who did a MS thesis with me in IISER Tirupati. He was a student of IISER Tirupati when he did this thesis. Now he is in this Marie Curie doctoral network, starting his PhD work in Naples, Italy. So both of them have done most of this work, and some of the references from where all these results are given in detail are shown here. I think I have not exceeded my time, so let me stop here. Thank you very much for your attention.
Yeah, thank you, Professor Ambika, for this very wonderful talk. And yeah.
So I think now I should stop sharing, no? Then only I will see the other one.
I don't know, you can see the Q&A even while sharing. Yeah.
No, I don't see that.
Okay, then maybe you can stop.
So let me stop sharing.
Okay.
Now we can see Q&A. Okay.
Yeah. Click on that, there are questions. And
So
I request the
how
audience.
do I do it? Shall I just start it or?
Yeah, I think you can start, and slowly the questions will come. May I request the audience to type your questions in the Q&A box.
So it says
you
before,
want to say something before?
I don't know what is before, but in your figure, we observe a sudden transition from IHSS to synchronized oscillations at a critical value. Could you explain in detail whether this transition could be described by subcritical Hopf bifurcation mechanism? How would you formally demonstrate the stability of the solution in either case? Specifically, what role do possible bistable regions or hysteresis effect play in relation to the observed abrupt change in amplitude? See, very lot of questions there, but I think I will address one by one. So the transition from IHSS to synchronized oscillation. So we can say it's a type of subcritical Hopf bifurcation because you have revival of oscillations from a fixed point. But now we are not having single system, but the systems are on a network. And we have inhomogeneous steady state, which means all these steady states are not the same. So this is not the same simple type of Hopf bifurcation, but in a way you can say the mechanism is the same. Now stability, there are different ways of showing stability. One case that I have done in our work is to do the Floquet theory. As you know, any limit cycle oscillations, we can apply Floquet theory. That I have also done in this case and shown that the synchronized oscillations that you get are stable. The other simple test that we can do is run it for a very long time. In fact, I have done it for a very long time, and then I have discarded almost 10⁻⁶ data as transients, and then we found that they are still there. Another way I have tested the stability is give it a small perturbation, either a small noise or some other perturbation, and then wait and see whether it goes back to the same synchronized oscillations. I could show that it will go back to the same type of synchronized oscillations even after the perturbation. Now, what role has possible bistable regions or hysteresis effect play in relation to this? See, one thing in this bistable effect is very relevant to in the case of chimera state, because we have specifically taken the case of Landau-Stewart oscillator, which has got 2 different steady states. And we have chosen carefully the initial conditions such that half of them have one type of one very near one steady state as their initial condition, the other half has in the other region. That is where the bistability plays a role, and that is where we find hysteresis effect are also there. I think that is what the question is. Now let me go to the next question. What is the meaning of synchronization error? See, how do we check for synchronization? One way is to plot this, either this, we have these spatiotemporal plots from which we can check whether all the oscillators are going together at all spatial locations also. That is one way. The other way is to check whether from the time series. But if you really want to quantify, we have to look for a synchronization error. So what we do is, we calculate the mean value of all the oscillators as X bar, and then take the difference of each of them from that, in a way standard deviation of that. And then time average it. We are not doing it at one particular time. For spread over the last part of this integrated output, you calculate this, average it over all the oscillators and over a definite interval of time. And then if all of them are moving through the same state in time, the synchronization error should be 0. So that is why we use it as a measure or a quantity to test or check for synchronization. Increasing noise strength shows the continuous transition is there. Any real world example which shows this behavior if increased noise strength? See, one can think of a real world example in the context of neurons, for example, but I have not worked out in this case how the sudden transition can become continuous as a real world example. We can think about a neuronal context itself or any of the other cases where sudden transition happens, but I have not applied it to a very specific case like a power grid or any other thing, but that can be done. Then the next question is, how does synchronization result depend on the number of oscillators? Okay. Actually, I have done for by increasing the number of oscillators, I have checked from 100 to 500 something. But other than that, I don't have a clear idea. How will it depend on the number of oscillators for chaotic dynamics? How does this result? Which synchronization result? Do you mean the sudden transition result or the overall complete synchronization result or the recovery of oscillations? Because I have shown different cases. I'm not sure, but maybe Norbert can show it, or otherwise in general, I will say, I didn't find any size effect. Onset of synchronization. Onset of synchronization from suppressed state, or in general by increasing the coupling strength, onset of synchronization. I didn't find any size effect. In fact, all these cases I have tried around 500 oscillators to 500 oscillators, and the size was not playing any role there. That's what I found. Maybe some specific cases it may be there, but I'm not that sure. Sorry. I think that's it, no? Okay, sorry. In high dimensional chaotic system, there is sometimes a dependence on the number of agents. Okay. Okay, so that's a good information. I was wondering whether the same for synchronization. Okay, high dimensional chaotic system, there is a dependence on the number of agents. Okay. So I have not checked about higher dimensional chaotic system. So that part I am not very sure. Okay, anyway, thanks for that information. Maybe I will check it. Thanks, Norbert.
Panelists also would have questions. I think the questions in the Q&A box are kind of done for the time being. Jürgen, you have any comments?
Yeah, maybe a question. Could you give some hints for neuroscientists to look experimentally for your findings, to confirm or to use for controlling some special cases or so?
So one thing is, if they can have this excitatory and excitatory and inhibitory coupling, which is actually what I considered as attractive coupling and repulsive coupling in the later stage also. So these two types of couplings are very relevant for neuronal dynamics. So if that can be done, and then they can have some sort of a coupling between them. So the only thing is, here what I have considered is synaptic coupling in each layer, but I have not considered how the coupling between them can be. There I have considered only feedback type of coupling. But in the context of neurons, for example, that coupling can be electrical. That's possible. Like diffusive type of coupling. That is something very easy to check also, experimentally also. And then one can see, as somebody pointed out, even how noise can reduce this sudden type of transition. That can also be checked. The other case that I find interesting in this context will be to consider the case I considered in the very beginning, where you have the network of systems as well as a network of dynamical agents, or what I called as environment. This has a real role in neuronal context because the second layer of environment can be astrocytes. And the first layer can be neurons. So between astrocytes and neurons, they can have a network of their own, and we know that they influence each other very much. So the role of astrocyte in controlling neuronal activity or activity patterns of neurons, I would say, is a good thing to check.
Okay, thank you. Thank
you. Yeah, I have a question, Ambika.
Yes, please.
So do you see any role of relay synchronization in brain dynamics? It's related to what Jürgen asked.
Yeah. See, actually, in the brain, most of the connections are unidirectional. For example, synaptic coupling actually is unidirectional coupling. So I think there is connection, because one context I said is different parts of this cortex. How does one part of brain, which is cortex, is related to thalamus? How do they connect? So I think there is relevance when you have unidirectional coupling. So even though two parts of the brain are not directly connected, through this thalamus, they can get synchronized. So that is the only thing I have read about. I have no clear details about that. But I think in the brain, it always happens, because even without direct connection, some part of the brain can get synchronized with the other part, etc. So that's happening. Yeah.
I have another question. Can you explain what is the difference between explosive transition and tipping transition?
I think it's almost the same, I would say. Tipping means a sudden transition.
Yeah.
So we normally consider explosive transition in the context of, I think it is always used in the context of synchronization. Systems suddenly all of them suddenly going to synchronization, which is, because it is so sudden, it is called explosive. But people use the term sudden also for it. Tipping is actually, explosive synchronization is one type of tipping, I would say. Tipping can be of different types, because it need not always be transition to synchronization. It can be various type of transitions, even from amplitude of oscillations to that state is also sudden, then it's a tipping. So tipping is a general term, that's my feeling, where any type of sudden transition that happens with a very small change in parameter or some small changes is tipping. And tipping, people say, can be of different types: bifurcation induced, rate induced, noise induced. All these types can happen. It can happen in single systems also.
And explosive can occur under what condition? Explosive transitions?
Explosive transition is also a sudden transition, but normally it is linked with the term synchronization. So a larger number of systems. See, the difference is, when explosive synchronization happens, the mechanism is very different from continuous type of synchronization. Because in continuous type of synchronization, a few systems get synchronized and slowly it grows and it becomes completely synchronized. But in explosive type, there is some sort of a heterogeneity or some perturbation or something which prevents the systems from systematically growing in size. So they remain as isolated clusters. And suddenly, when it crosses some value, these clusters all unite. So there is an underlying difference in the mechanism.
Okay.
But explosive is normally then used related to synchronization. And tipping is a very general term. Explosive synchronization, I would say, is one type of tipping.
Okay, thank you.
Now, one more question in the question answer now. Is the amplitude depth obtained for large coupling in one layer observed for all the units in that layer? Yes. It's a synchronized amplitude, because we have said two types: inhomogeneous steady state and homogeneous steady state. But homogeneous steady state means all of them are in the amplitude death state, and they are all in the same amplitude death state. Inhomogeneous steady state is also a death state, where we find there are two steady states are possible for this Landau-Stewart oscillator. So some of them are in one state and some of them are in the other state. But anyway, they are all amplitude death state. That is happening for all of them in the same layer. I think that answers that question.
Last question. I have a
Yeah, please.
comment. We see this transition from, if you increase the noise, we see transition in our combustors from a explosive state to a continuous, explosive transition to continuous transition when we
By increasing what?
the noise levels, by increasing the turbine.
Oh, I see. Okay.
We have done that.
Mm-hmm.
The second thing what you showed, which I find very attractive, but I don't know.
Yeah, exactly. That's what I have also just now said. And somebody asked a question about its practical situation.
So we have a lot of seen it in practice.
Oh, that's interesting.
The comment I have is you showed that you can control the explosive transition and
Yes.
make it a continuous transition.
Yeah.
This could be really life-saving for all the machinery, because explosive
Correct.
transition
I think that will be very relevant in your context also, because you don't want an explosive
know
transition.
how to change the coupling constant, etc. In model, I can see what you change. In our experiment, it's not very trivial, but it has given me some food for thought to figure out how.
Correct. And I would say in a practical situation like that, rather than tuning the strength of coupling, applying noise is very easy, no? Do you think so?
Noise is inherently there, and we can actually increase the level of noise by certain ways, actually. By there are some ways to generate more turbulence. So I think that would be probably the way. Yeah. Any other questions? I think that's.
I don't see any other question. No, let me just check question.
No, I think that's all the questions.
There's nothing there. I think that's it, no? So I
so
think we finished fast, no? Was it very fast, Sujit?
No, very good. I really enjoyed it. I understood a lot of things.
Normally, I have a tendency to be very fast, and so I'm being careful always, but still.
A fantastic talk, and thank you very much for the wonderful talk.
Okay.
Thank you.
We are very pleased.
Thank you all for joining, and thanks to see you all again.
Yeah. Our next webinar will feature Professor Clement Ivanov from the Keck Laboratory for Network Physiology at Boston University. There's a slight change. The talk is on Thursday, May 29th, and not on Monday. It's a Thursday at 8. I will send the links to everyone. Sorry about this change, but there were some issues.
Yeah. Okay.
So we'll see you all 1 month later. And
thanks Jürgen for joining, and thank you for he left. Thank you for agreeing to come to CNSD. I was going to say he left before that. He has agreed.
Wonderful.
Next to CNSD, we are hosting here in ISA Trivandrum.
Awesome.
Yeah. Okay, then.